We are discussing electric circuits course of second semester students, and this is our textbook. I am Dr. Khalid Emerson in the Department of Electrical Engineering, UET Lahore. In this lecture, uh, we'll discuss chapter 7, and this is part 2 of my lecture on chapter 7. Note that only first order circuits are included in this course. This is the title of chapter 7, first and second order. But we'll discuss only first order circuits. Second order circuits will be discussed in the next semester. So I have already uploaded part 1, these three sections, and in part 2 I will discuss first order circuit response to exponential and sinusoidal inputs. Now the first order response to exponential inputs. This is a first order circuit. We have only one energy storing element in it, and this is the circuit which excites this capacitor. Whole circuit may consist of more than one resistors and more than one sources, but here in this circuit we represent the Thevenin equivalent of the source circuit. The differential equation we have already discussed in part 1, and the right hand side is the voltage source multiplied by UT. It means that the voltage, this source is equal to 0 prior to t equal to 0, and after that it is Vt. Now the natural response of this differential equation is the solution of the homogeneous equation, and you know this is the solution of homogeneous equation, which is known as natural response, and we have discussed it in part 1. The forced response or particular response depends on the forcing function. This is the forcing function, means the excitation. What is the type of excitation? It may be a constant voltage, it may be exponential voltage, it may be a sinusoidal voltage. So the forced response depends on the type of this source. For forced response, we have to consider the excitation Vt. Now UT it is not necessary to use UT over here. We assume that this Vt starts from t equal to 0, and prior to t equal to 0 it is 0. So this equation holds for t equal to or greater than 0. When we mention this t, there is no need of showing UT with it, unit step function with it. Now the forced response will depend on the form of the forcing function. Forcing function, I will repeat again, this is the forcing function. It may be a voltage source, it may be a current source, and the form of forcing function. If the forcing function is a constant voltage, VA, the forced response will be a constant. The form of the forced response will be constant. If the forcing function is exponential, the forced response will be another exponential. And if the form of the forcing function is sinusoidal, represented as the cosine omega t or sine omega t, or sum of cosine and sines, whatever form, all are sinusoidal waveforms, or the form is sinusoidal, the forced response will be another sinusoid. We can express it as A cosine omega t plus B sine omega t, or as we have discussed in chapter number 5, we can express it uppercase A multiplied by cosine omega t plus theta. Now for an exponential input, this is exponential input, and from the previous table, well, this is the natural response, we know it already. For the force response, we select the force response an exponential type, because the forcing function is exponential, and as you have seen a table in the previous slide showing the form of the forcing function and the form of the forced response. Because the forcing function is exponential, we select the forced response as another exponential. In this exponential form, this alpha will be same as that of the alpha in the forcing function, and we will determine kf, the coefficient kf. Now we substitute this forced response, assumed force response, into this equation, and when we substitute it and then we proceed, we take derivative of it, and then the remaining terms are as such, and then we reach this minus alpha kf RTC plus kf is equal to VA, as the common term is E minus alpha T, E minus alpha T, E minus alpha T. So this term is cancelled on both sides, leaving this. And this equation gives us kf, which we need to determine kf over here. So if we find kf, then our force response is now final. Now, as we know that the total response is the sum of natural response and the forced response, this is the natural response, and the forced response kf E minus alpha T, and we have determined kf, and alpha is same as that, it is exactly same minus alpha, so this is the total response. So in here only one thing is unknown, k. In order to determine this k, we use initial conditions. For initial conditions, we substitute t equal to 0 in this equation, t equal to 0. If we substitute t equal to 0, so t equal to 0, in here only k, we'll get only k from here, and t equal to 0 over here. So we'll see the k is, this k is equal to V naught minus this term, as e raised to the power minus alpha 0 or minus 0 is 1, e raised to the power minus alpha over anything is 1, therefore k is. Now as we have determined this arbitrary constant k, we can express the complete response as k e minus t over the time constant plus VA over 1 minus alpha RTC, and as shown. Now note that this alpha is the same as that we have seen in the forcing function. Now I think it is just the repetition, and then we express the response in this form, as we have determined k over this k, this k, this is k over here, and this is the complete response which holds for t equal to or greater than 0. Now we discuss an example. In this example, this is the circuit which is exciting this, and only one voltage source is shown, and this voltage source is an exponential voltage source, or the form of the forcing function is exponential. 100 is the coefficient and alpha is minus 1000. We will determine VC. Note that capacitor voltage is the state variable related to this capacitor. Knowing this capacitor voltage, we can find capacitor current, as IC is C multiplied by dVC by dt. If we determine the current, we can determine this current as well, because this capacitor and resistors are in parallel, and the current will be voltage VC, which we have already determined, divided by 200k, and the current flowing through this 300k ohm resistance or current supplied by the source will be sum of these two currents. So only knowing the state variable we can determine the remaining voltage and currents for all the circuit elements. Now in here we have one capacitor and more than one resistors. In order to determine the time constant, we have discussed it in the previous lecture. We will see what is the Thevenin resistance seen by the capacitor. In doing so, we eliminate the voltage source. Eliminating the voltage source means we short circuit the voltage source, and the resistance seen by this capacitor is 300k ohm resistance in parallel with 200k ohm resistance and R equivalent. This is the R equivalent parallel combination of this, and the time constant is R multiplied by equivalent resistance multiplied by C. Note that here you need to do some correction over here, so I will do it for you. So consider this as this is R equivalent, which we have determined over here. This is R equivalent multiplied by C. I wanted to write this over here, so I think it will not be a problem for you as I have explained it over here. So R equivalent multiplied by C. So this is the time constant. I advise you to verify these calculations. There may be, if in case of any error in it. So 1 over Tc is over here, 1 over Tc, and VA is 100, as this is VAE minus alpha T, and alpha is 1000. Now you should be able now to find capacitor voltage and capacitor current. As we know, V naught, VA, alpha, RT and C, I think you will not find any difficulty in slightly different notation. RT is the Thevenin equivalent of resistance seen by the capacitor. Here I have used R equivalent. So basically R equivalent and RT are same thing. So we can find the capacitor voltage. Knowing the capacitor voltage, we can find the capacitor current. Now first order circuit response to sinusoidal inputs. When the input is sinusoidal, for t greater than or equal to 0, this is the forcing function, and due to the table which we have discussed in a previous slide, we will select the forcing, due to the forcing function, we will select the type of the forcing or form of the forced response. Here, this is the natural response, which is the solution of the homogeneous equation with right hand side is equal to 0. It is same, we have discussed it before. And for the forced response, due to the form of the forcing function, we select this forced response. And this is the coefficient of this cosine is VA, but here it is VF, and frequency will be same, cosine, and this is cosine, and there may or may not be some this the phase angle over here. So we express it as cosine omega t plus pi. From chapter number 5, you know that a single sinusoidal function can be expressed as sum of two sinusoidal functions with coefficients a and b. And now we substitute this Vf in this equation. So RT d by dt of Vf plus Vf, which is as such, and the right hand side is this. This is the forcing function. We proceed further, take derivative of this, then proceed further, and from here we find what is A and what is okay, comparing coefficients. I think there is some Okay, so in this equation, just comparing coefficients of sine and cosine, compare the coefficients of sine with the sine. So this is minus omega A RTC. It is minus omega A RTC, minus omega A RTC, and plus B, and there is no sine term at the right hand side. Therefore, this right hand side is 0, and the cosine, coefficient of cosine, omega B multiplied by RTC, omega B multiplied by RTC. There is another cosine over here, plus A, and at the right hand side there is another cosine function over here, and therefore the right hand side of this equation is VA. We proceed further, and from here we can solve these two equations to find A and B. And then knowing A and B in our assumed form of the forcing function, A cosine plus B sine. So this is A cosine plus B sine, and we end up over here. This is our natural response. Now this is the complete response. Natural response plus the forced response for t greater than or equal to 0. Now only one thing is unknown. K is an arbitrary constant. We can determine this K by applying initial conditions. We will discuss in the next slide. So for initial conditions, we substitute t equal to 0 in it. If we substitute t equal to 0, we can find K as shown over here. Substitute t equal to 0, only K will be left in this term, and t equal to 0, the second term will be 0, and t equal to 0, cosine of 0 is 1, and only this thing will be left. So here we will have K plus VA over 1 plus omega RTC whole square equal to V at t equal to 0. So V at t equal to 0, we use it symbolically as V naught. So from here we can find K. Knowing the value of K over here, this is the value of K. This is the complete response. In this complete response, this is the natural response, and this is the forced response. Response in amplitude and phase angle form, from chapter 5, we know that we can express it in this phase angle and amplitude. This is the amplitude and this is the phase angle. This is only one sinusoidal function, and we have sum of two sinusoids. You know that we can express it in this form, where theta is tan inverse of minus b over a. So our b and a, you can verify tan inverse. Our b is omega RTC, and a is 1 in here. A is 1 and b is like that. So first order response circuit to sinusoidal input. This is as we have this from the previous slide. This is the complete response. Now, response to an RL circuit. This is the response of an RC circuit. RL circuit, you can follow a similar procedure in order to find the response of RL circuit. Response of RL circuit means the current flowing through this inductor, because current is the state variable. If we write differential equation, which we have seen before in the previous lecture, knowing this, the source form of the source is the sinusoid, we can find the complete response as this, and this is the natural response and this is the forced response. I will advise you to go through all the steps which we have discussed for RC circuits. Now it is RL circuit, only the different form of the differential equation for this circuit is same. Only difference is in coefficients of all terms. You should be able to conclude this, to understand this. Now, This is an interesting example. In this example, we have a sinusoidal excitation, IA cosine omega t. This is the sinusoidal excitation, and there is a switch over here, and the switch is normally closed, and the switch is opened at t equal to 0. With this knowledge, we can determine the initial conditions or initial value of the state variable of IL. State variable is inductor current. We can determine this IL at t equal to 0, and note that this initial condition is essential in order to find the solution or in order to find the response. As we have discussed before in the previous slide, this is the response or solution of this circuit. And what is the solution? We want to determine the current over here. This is IL. Though it is shown as I, but it is IL. So IL, I and IL is same. This is IL. You have seen it in the previous slide. Now, how to determine initial conditions? Now, assume when the switch is closed. When the switch is closed, the whole current flows through this. The whole current flows through the switch. Whole current flows through the branch consisting the switch over here, and no current flows through this. Whole current is flowing through this branch, and no current flows through this resistance, and no current flows through this. Therefore, okay, and when the switch is opened at t equal to 0, when we open the switch, then no current will be flowing in this through this branch as we open the switch, and then this current will be diverted to this part of the circuit. Now, as before opening the switch, the current flowing through was 0, and a discontinuous change in inductor current is not possible practically. We have said it before in the previous lecture that a discontinuous change in the inductor current is not possible. And in capacitor, discontinuous change in voltage is not possible. So, the current before and after the closure of the opening of the switch will remain same. So before the opening of the switch, the current is 0, and just immediately after when we open the switch, current will remain same. Therefore, the initial value of the inductor current or the state variable, symbolically represented as I naught, is equal to 0. And initial value, this is the complete solution, and initial value of the inductor current is 0. Therefore, this is the complete response. The remaining things will remain same in this response. Now, it is reproduced again. First term in the above expression decays to 0 as t approaches infinity. Note that cosine function will never decay to 0 because it is a continuous function, and it is a periodic function, and it will be oscillating forever. But as we have a exponential term over here, and power of this exponential function is minus t divided by the time constant, as t approaches infinity, this will diminish as t approaches infinity. So this term will diminish with the passage of time, and the remaining part of IL will be this. So we will call it steady state response. Steady state response. When the transients will fade away, this will remain, and this is known as steady state response. Steady state response, therefore, IL is only the second term in this solution. And the inductor voltage, in this example, I have taken this example from the textbook. and we need to find the output voltage, which is the inductor voltage. You know that if we know the current, the inductor voltage can be determined, or vice versa, and the inductor voltage is L di by dt. We know that L di by dt. As we know IL, this is IL. If we differentiate IL with respect to time multiplied by L, we have this. Here, you may wonder that IL is a coefficient of a cosine omega. This is the coefficient, and then multiplied by cosine omega t plus theta. And if we differentiate, we will have minus omega sine omega t plus theta. But here I have written cosine omega t plus theta, and negative, you can't see negative sign over here, because it is the output voltage is expressed in the form of a cosine function. You know that we can convert a sine function into cosine function by a shift and angle, and here the theta is tan inverse of r over omega L. So this may be a teaser for you. You may feel it uneasy over here. Yes, I know that, but I will advise you first to differentiate this. It will be a sine function multiplied by L, sine function with negative sign, and then after a little struggle, you will find this as the output voltage, because we want to express it in cosine function. There is no harm in expressing, leaving it as such. If we differentiated minus omega sine omega t plus theta, but theta with the sine function will be different from the theta with the cosine function. I will leave it to you. I know that you will take quite some time, or few of you may do it in few minutes, but many of you may take some time. Take it as a good mathematical exercise or a little challenge to reach this. If you have any question, you can always ask me, or the teaching assistant is also available to help you. Now with this, we complete part 2 of lecture on chapter number 7. This is the title of the second of chapter 7. Only first order circuits are included from section 7.1 to 7.4, and you all are advised to attempt the end problems related to these sections. Thank you.